Hello, I'm Miika Rämä from VTT Technical Research Center of Finland, holding you a presentation on design and operation of a district heating system. The presentation contents. First, I'm going to describe the basic design process, then give some details on designing production and the concepts of heat load duration curve and combined heat and power production. Then I'm going to talk to you about designing distribution network, then something on operational optimization of production, and then finally we'll conclude with a summary. So this slide represents the basic design process of a district heating system. While this is compiled from a perspective of designing a new system, a renovation or an extension of an existing system is a very similar task. So first step is to assess the heat demand of the consumers. Usually heat demand is evaluated as a year-long hourly time series in order to capture both peak and temporal variation of demand. This is used as the main input for overall district heating system design. Heat demand itself and/or the consumer systems for internal heat distribution might already set some constraints for the required temperature level, which has a direct effect on designing the distribution network, for example pipe sizes, and finally on the heat demand experienced at potential production sites with distribution heat losses included. The production might benefit from a heat storage, which can affect the dimensioning of a distribution system and designing the production. The process is iterative. While consumer heat demand remains the same, there are a lot of dependencies between alternative design choices, for example between temperature level and production output. In the end, feasibility of a system is assessed in a techno-economic analysis. Other alternatives also exist, such as share of renewables in production or self-sufficiency. Usually, the final decision on the design is made based on several key indicators and greatly depends on the system in question. So heat load duration curve is one method that can be used in designing of production for a district heating system. It is a year-long hourly time series sorted from highest to lowest value. It can be used for evaluating reasonable capacities for different kinds of production technologies and/or as a visualization of the design. The process starts from the sorted heat demand time series, the demand to be satisfied. Baseload capacity comes first. On top of the baseload capacity, some form of variable source of heat is needed. Peak or backup capacity is utilized when demand exceeds the capacity of the baseload and variable production, or when the demand is below the minimum production capacity of a baseload plant. There also might be some uncontrollable heat sources, such as solar heating in the system. This example shows the different roles of alternative sources of heat might have. In real life, the shares and periods of utilization vary. For example, heat storage or characteristics of available technologies can easily change how different heat sources are utilized. Combined heat and power production is a very efficient solution for supply of both heat and electricity, well worth a separate slide. CHP is often used as a combination of baseload and variable capacity, if you recall the example from the previous slide. CHP can be considered to be an integral part of the most efficient district heating systems. Considering separate production of heat and electricity, CHP is approximately 33% more efficient, fact visualized right here. These Sankey diagrams compare combined heat and power production to separate production of heat and electricity. Significantly lower losses in conversion can be observed. In CHP production, steam exiting the steam turbines and/or flue gases are utilized in production of heat. Overall efficiency is an important indicator, but for CHP, power to heat ratio is a key indicator as well, as one usually wants as much electricity produced as possible. Modern plants can have efficiencies of over 90% and power to heat ratios of over 1, further improving the example given in the Sankey diagrams. Distribution network is focused on pipe size definition. The network represents a large share of the investment costs and is therefore a significant part of evaluating the feasibility. Pipe sizes are defined by peak heat demand of each consumer, the chosen temperature level, that is the temperature difference at each consumer at design point, and reasonable pressure drop, usually defined by the structural pressure of the pipe material used. Heat losses and pumping costs form the operational costs of a distribution system. Smaller pipes have lower heat losses but higher pumping costs. Heat losses are usually the more relevant factor, but this depends on the value of heat and electricity in an investigated system. Investment costs are paid based on pipe sizes and lengths as well as insulation thicknesses used. The costs consist of material, excavation and pipe work. In Finnish district heating investment cost statistics, their respective shares are roughly 25%, 50% and 25%, although this depends on the size and type of the pipe in question. In larger pipe sizes, the material costs become more important at the expense of excavation costs. Operational optimization tells us how to operate the heat production as efficiently as possible. This optimal operation depends on the following inputs: value of commodities, electricity, heat and fuel prices, and their predicted or known variation during the optimized periods. Status on the possibly available heat storages, that is the fill factor. Forecast of the heat demand and production by uncontrollable heat sources. The process is usually carried out by a dedicated optimization model, which is a mathematical description of the system, often implemented in linear programming or mixed integral linear programming. The model is usually run with hourly time steps. The week-long example here shows how the predicted heat demand should be satisfied. First, the heat losses of the distribution network are added to the consumer heat demand. Utilization of CHP unit of a specific capacity depends on market prices of electricity and the heat demand, making use of possible heat storage capacity. Storage is used as the primary heat source to fill the gaps left by the CHP unit. Finally, peak and backup boiler is supplying the remaining heat. Then, with the summary. Heat demand is the most important input for the design process. System specification after the heat demand evaluation is an iterative process due to the fact that its elements have relative dependencies. Heat load duration curve is a useful tool for production design process as well as for visualization purposes. Distribution network has a significant impact on the investment. Operational optimization can improve the system efficiency. This is especially true in a more complex operational environment with, for example, multiple sources of heat, active commodity market, and often when utilizing heat storage. Thank you for your attention.